Hello, everyone, and welcome to the video key for the synthesis activity. Again, the activity is meant to be lecture support, so I didn't provide a lecture video because you've been attending your lectures. Um, and so hopefully you were able to work on this and get some extra practice with synthesis, which will help you in your lecture course. Let's head on over. And start working on the activity. All right, so we have provide a concise synthetic route for the following transformations. Show all synthetic steps separately. Okay, so for this one, it looks like we want to functionalize this position, and maybe we can eventually do a Grignard to add another carbon here. But to start with, hopefully you might have remembered a reaction which will allow you to do allylic halogenation. And so the conditions for that are NBS and heat or light. And that's a radical reaction. And then this will nicely set us up to be able to do eventually to do a Grignard reaction. However, if we end up using this as the alkyl halide in the Grignard reaction, we would end up with an alcohol that's one carbon away from this because the other component would be the aldehyde. We actually need to convert this to the aldehyde component in order to only add one more carbon. So what we want to do is we can do a reaction where we first convert this to an alcohol, which can then allow us to convert it to an aldehyde. And then once we're at this aldehyde stage, we'll be able to add one more carbon to a Grignard reaction. And then lastly, we can add in this extra methyl through a Williamson ether synthesis. So let's go ahead and add in the reagents necessary to do these reactions. So this is an SN2 reaction to convert an primary alkyl halide to an alcohol. We just need to use a strong nucleophile, such as hydroxide. And then oxidation of a primary alcohol to an aldehyde can be accomplished with PCC. From here, we want to do the Grignard reaction to add on this extra carbon. We will treat this with methyl magnesium bromide, followed by an acidic workup. Which the acidic workup will give us this protonated alcohol. And then the Williamson ether synthesis involves the use of a strong base, followed by whatever alkyl group we want to add, which in this case would just be methyl bromide or methyl iodide. So we can utilize a strong base, and we could use sodium hydroxide, but we could also use a stronger base in order to fully deprotonate the alcohol. So for example, we could use NaNH2 followed by methyl iodide. And again, that's a Williamson ether synthesis. Let's look at the next problem, which involves converting bromobenzene into this aldehyde with 2 additional carbons. Looks like we're going to be making a carbon-carbon bond, so it might be a good idea to think about doing a Grignard reaction. But because we have a relative positioning where the carbonyl gets introduced at carbon 2 away from the new carbon-carbon bond being formed and not carbon number 1, we actually want to use an epoxide instead of an aldehyde. So we are going to convert, and again, we're going to use an epoxide. That will allow us to get an alcohol where again, that alcohol is at carbon 2. And the conditions here are formation of the Grignard with magnesium. Remember, that will insert in between the carbon halogen bond. Then we're going to use just ethylene oxide so that we can get our 2 carbons added with the alcohol at the right position. And then we're very close to final product. We just need, again, to oxidize the primary alcohol to an aldehyde. Oh, and I should have written in a acidic workup, which is always necessary for Grignard reactions. The next problem, it looks like we're going from something with 3 carbons to 5 carbons. We want to think about possibly doing some sort of carbon-carbon bond forming reaction, which could involve a Grignard, but in this case, I actually want to use alkylation of a terminal alkyne. I think it will be a more straightforward process. But before we get to that, we need to think about reacting this alkane. And whenever you start with an alkane, the first thing you want to do is a radical halogenation reaction, because there's no other reaction we can do with an alkane. And when we do this radical halogenation reaction, just note that the bromine is going to go on the most substituted carbon preferentially. This is the regioselectivity of that reaction. We would actually prefer to have the bromine at the terminal carbon, but radical halogenation will place it on the more substituted carbon. However, we can do a series of reactions to actually move it to the position that we want. So we can do an elimination addition sequence in order to move the halogen to the less substituted carbon. This is an elimination. Because the 2 beta carbons are equivalent, we don't have to worry about Zaitsev versus Hoffman selectivity. However, we do want to make sure that we don't get a lot of SN2 because it is a secondary alkyl halide, which can do some substitution as well as elimination. So it actually would be better to use a bulky base just to shut down SN2 and promote elimination instead. From here, this is an addition reaction. It's a hydrohalogenation because we end up with a hydrogen here and a halogen there. So in order to do a hydrohalogenation that goes anti-Markovnikov and the bromine ends up on the less substituted carbon, you need to introduce some peroxide into that reaction. And then from here, we're actually set up to be able to add 2 more carbons, but we'll just use an alkyne and then eventually get an alkene. So for example, what we could do at this point is to add in those 2 more carbons, but add them in as an alkyne. So I'm going to add in 2 more carbons, making sure not to draw this as a bent, right, structure. And then we will be able to reduce the alkyne down to an alkene. So this just utilizes a deprotonated alkanide ion, do an SN2 reaction, and then we can reduce an alkyne down to an alkene. We want to be careful because we don't want to go all the way to the alkane, and if we used regular hydrogenation, we would get the alkane product instead of the alkene product. So instead of that, we can either do hydrogen with Lindlar's catalyst, or in this case, we could have used sodium and liquid ammonia. Remember that hydrogen with Lindlar's catalyst gives a cis-alkene, and sodium with liquid ammonia gives a trans-alkene. But in this case, there's no stereochemistry, so we could just use either one. Let's look at this next example. If we look here, we actually are not introducing any additional carbons. We have 4 carbons in the product and 4 carbons in the reactant. So we don't need to necessarily think about adding in additional carbons. But this actually is a pretty tricky problem right now. Once you guys learn more chemistry, it will become more straightforward. But for example, we could introduce we could do a hydration reaction, right? And then I'm just going to kind of do like sort of a dashed line, okay? Because, oh, actually, you know what? This was covered, pretty sure this was covered in your alcohol chapter, now that I think about it. So no dashed line necessary. For some reason, I was thinking it was covered later in the semester, but I think you guys have covered it, which will be great. So it'll be fairly straightforward. Okay, so again, an anti-Markovnikov hydration reaction, because we end up adding hydrogen and OH, so overall water across the double bond. But the OH ends up at the less substituted position, so we call that anti-Markovnikov. So if you recall, the way to do anti-Markovnikov hydration is through hydroboration oxidation. And you just have to memorize these reagents to be able to do that. And then we can oxidize a primary alcohol all the way up to a carboxylic acid using sodium dichromate under acidic conditions. Right. Next, we want to, this one talks about using a convergent synthesis. The idea is that we can make two different components and then react those together to make a product. So if we think about the retro Diels-Alder reaction, right, how we can go back to the reactants and make this through a Diels-Alder reaction, perhaps that one of the components was the diene and the other one is the dienophile. So perhaps for A, we should be targeting 1,3-butadiene and then the dienophile, which would be that structure. So again, our target will really be this, and then we'll do some heating in order to do a Diels-Alder reaction to produce the product. All right, so let's think about how we could make A, starting from butane. So if you recall, what did I tell you guys about starting from an alkane? Right? We only have one choice. You have to do radical halogenation. Right? And the bromine has to go on one of the more substituted carbons. Even if we didn't want it there, that's where it's going to go. And then from here, let's focus on trying to get one of these into an alkene position. So if we wanted to eliminate it to get an alkene, we can do an elimination reaction. In this case, the two beta carbons are different, right? So we do need to worry about Hofmann or Zaitsev regioselectivity. So recall that if I used a small base, I would have gotten the Zaitsev product, which is the alkene and the more substituted position. And then if I use Hofmann conditions using a bulky base, I'll end up with the alkene that I want, which is the less substituted alkene. Right, so we want to use a bulky base in order to get Hofmann regioselectivity. And then from here, we can work on basically doing the same thing, very similar anyway, where we want to get a halogen and then do an elimination of that halogen. So how do we do that? Right, so now that we have a double bond here, now this is considered an allylic halogenation. In this case, instead of bromine, it would be better to use NBS to prevent the side reaction of bromination of the alkene. And then again, we'll use our bulky base to eliminate it to get the 1,3-butadiene. So this one is A. Okay, we've accomplished A. Let's think about how we might be able to get B, right? Now we have an additional double bond to an oxygen that we need to think about. So we actually could start out the same way and get to this intermediate. And then if there was a way to potentially convert this to an alcohol, right, then we could just oxidize this to a ketone. So this is a substitution reaction, right, an SN2 reaction. So we want to use strong base. And this is an oxidation reaction. We can use PCC or sodium dichromate. And then again, we would take those A and B together, gentle heating to do the Diels-Alder reaction. Moving on here, right, hopefully you might have thought of doing carbon-oxygen bond cleavage, right? Because we are starting with an ether. And one of the few things we can do with an ether is to cleave the carbon-oxygen bond. So we can definitely do that. Again, that was in the ether chapter that you learned that reaction. It will not be able to cleave this bond because this is an sp2 hybridized carbon, but it can, right, cleave that one. So what will end up is this 3 CH2s and a halogen. And depending on whether or not you use HBr or HI, you might have ended up with a bromine or an iodine here. So excess HBr, really, you only need one equivalent of HBr actually. So HBr and heating, it will give us this product. And then from here, it looks like we need to make a carbon-carbon bond, right? Forming reaction. And we end up with a tertiary alcohol. So what we can do is we can do a Grignard with a ketone and get directly to that product. Oh, you know what? I forgot about the fact that right now this is not protected, right? So I probably should have to redo this because it's getting a little ugly here. But let's protect it first. So TMS chloride and pyridine will protect the OH group, because remember that will become a problem if we try to do a Grignard reaction. Now we're set up to be able to do the Grignard reaction. And the reagents for that would be magnesium, followed by the ketone, followed by an acidic workup. And then last step, we can do a TMS deprotection with either acid or trying to think of what the heck else do we use. Not HF, is it? It's TBAF. Tetrabutyl ammonium fluoride, right, or H3O+. We'll get rid of that TMS group. Okay, lastly, we have a ring cleavage reaction. And the only way we really know to break a bond is through ozonolysis. So I'm going to target ozonolysis as a key reaction in this sequence. But because we're starting with an alkane, we need to start with our only reaction possible, which is radical halogenation. The substrate for ozonolysis is an alkene. We can focus on doing an elimination such that we can then do ozonolysis of that double bond and cleave that carbon-carbon double bond. First, We don't have to worry about Hoffman or Zaitsev because the two beta carbons are equivalent. We'll just use a bulky base to prevent substitution. And then the conditions for ozonolysis of an alkene are ozone and followed by dimethyl sulfide. That will end up cleaving both of these two into carbonyls. So we'll end up with two aldehydes because of the hydrogens attached here. And then 1, 2, 3, 4 methylenes in between. We're trying to get these to look kind of like the product here. I'm going to draw my first aldehyde. They're facing the same direction. And then go 1, 2, 3, 4, followed by the next aldehyde. Now we just need to convert these aldehydes into ketones. And the way to do that is through a Grignard reaction. We can just use excess of the Grignard reagent. In this case, it should be an ethyl Grignard because we're trying to add an ethyl group. Right, so we have excess ethyl magnesium bromide followed by our acidic workup. That will end up giving us secondary alcohols, which we can oxidize through excess PCC to the two ketones. All right, hopefully you guys found that useful to get a little more synthesis practice for your lecture course.